Okay, good evening, everyone. So nice to meet you guys. My name is Tsinghua. I work in State Key Lab of Tribology. I came from Department of Mechanical Engineering, Tsinghua University. So it's my honor today to give you a lecture about the application of wind tunnel in racing sports. Okay, so quite a lot of contents today. First, I will introduce what is a wind tunnel. So, secondly, I will introduce a worldwide application and current state of arts in China. After that, why we use wind tunnel? Because we want to reduce the drag. So we will talk about air drag, the basic principle of air drag. Then I will give you 3 instances and give a conclusion. All right. So one thing is some part of the contents should not be take photo or films. Thank you. All right, what is wind tunnel? Very straightforward. Wind. We have a big motor, to generate wind, give the power. And we have a tube. It's large enough, so it's a tunnel. We call this tunnel. And in reality, for example, we do a car experiment. The car is running, and the wind air is relatively steady. So, and the wind tunnel, the car is steady, the air is moving. So we can measure the forces, we can check the flow field, and we control the airflow with speed, angle, pressure, temperature, humidity, and ionization sometimes. The equipment of wind tunnel usually contains balances we use to measure the force, and the particle image velocimetry, the PIV, to visualize the field. And we have smoke flow to visualize the field again, and sometimes we have a roller because the ground is steady or ground is running, it affects the drag. So sometimes we have the roller, the car is really moving on it, but steady from the outside. Okay, this is a wind tunnel. For the types, there are mainly 2 types. One is blow down. The blow down wind tunnel, and the second one is looped, or we call it recirculated or circulated. The air goes into the inlet and accelerate by the motor and blow off. The other one, air is recycling inside. For the work section, there are also 2 types. Is open, one is closed. Sometimes the wind tunnel can change their workstation because like this, see the white one is the closed work section. Or we can remove it, add a collector, and it's an open one, so it's changeable. Okay, and some wind tunnels have special equipment like the icing window or ionization window. The first one is usually used in the aircraft, the second one is in the space. Okay, so wind tunnel has been widely used in architecture, automobile, aeronautics, astronautics, disaster simulation, entertainment, and currently the sports. So the wind tunnel in the sports have many advantages. We have plenty of time. If the athlete is on the field, maybe he runs really fast, we cannot do measurement, or we cannot observe his gesture. So we have plenty of time in the wind tunnel. And also, the force is measurable, and for some sports, it's safe. We can see it in the later. Okay, the disadvantage, the wall effect, because actually it's it's a problem for all the wind tunnels. We have to consider wall effect because near the wall, the wind speed is not accurate. The second one is block ratio because human body's projected area is quite large compared to some early built wind tunnel. So this blockage ratio should not be over 3%. Maybe we can allow it to 7%, but no more. And we have to use some supporting structures. Some are used to fix the equipment. Some are used to make the athletes steady. Because even athletes, their muscle is still shaking. This shaking can be affect the force, the signal. Okay. So in sports, we can do drag optimization, team formation, equipment development. And the problem is unsteady human body. It's setup change. Every time we change the setup or change the athletes, the data will change a lot. And supporting structure, somehow it will affect the flow field, so it will affect the drag. All right, let's go to the second part, current state of the art. United Kingdom, they invest a lot of money in the cycling sport. They spend about 30 million pounds per year. And check the Olympic medals. 2004 to 2016, it increased. And on the other side, Australia, well, cycling 6-0. Rowing and canning 1-7, 1-1. However, UK is 1-3-6, keep increasing. And here, the University of Southampton is one of the one of the most famous university in sports science. And it's the base of cycling team of United Kingdom. This wind tunnel is called R.G. Michel. Okay, it's built in 1920, really, really early, and started using the sports. It's donated to the university in 1980, so we're quite really, really early. On the other side, Australia found this problem, so they start to do wind tunnel again. They start to do wind tunnel too. RMIT, they have an industrial wind tunnel, and they use it to do the bobsleigh. It's a 50% scale, a smaller one, because if it's a full size, the block ratio will be too large. And they use smoke flow to visualize the field, and they use wall tufts, 就是毛线绒. So wall tufts can be used to visualize it. It's very useful and cheap. Switzerland, RUAG has a aerospace center. This is a company focused on the space technology and defense technology, so they have their own tunnels. And it's a looped tunnel with closed attack section, really large, 7.5 times 11. Okay, it's huge. It's huge. And people, athletes do the snowboard and skiing test inside. The Netherlands had Dutch-German wind tunnels. It's a group of tunnels. One of them is LSD low-speed tunnel. They use it to do the cycling test. We can see a lot of supporting structure here. Actually, it's on the front of the it's in the front of the athletes, so it will affect the drag number. Okay, Canada. Canada found a program called On the Podium. Yeah, and the funding is 111 million Canadian dollars. Sorry, it's funded in 2005, and they have a bunch of wind tunnels. Most of them belong to university and our National Research Institute. So they test the skeleton, clothes, gestures, team formation, and they use wind flow, the smoke flow, wall tufts, and do this. So Brownie is also an expert employed by our country. Yeah. Japan, University of Tsukuba has a wind tunnel, and they do downhills. Also, there are some companies wind tunnel is open to the athletes, like Audi in Germany, and Specialized in US. Specialized is a famous bicycle brand. They have their own wind tunnel to test the bicycles. And also Belgium has a Flanders bike valley. All right, so this is in the world. What do we have in China? Don't worry, we have even better one. Okay, so first, little brother. We have two of them. They are movable. They can be transported by truck. Yeah, so they can be transferred from one base to the other base, one city to the other city. to accompany the training program of athletes. Okay, so it has 6 component balances. It has cable for ski jumping, and it has a rolling stage for skiing and skating. All right, this is a picture of that, and it's a ski jumping training. And the older brother, large one, is very special. Yeah, it's 1 year ago, it's still nothing, but now it's already put into use. Why is it special? It has 3 closed workstation, and it can be used simultaneously. Have 0, 11 degree, and 32 degree. Why? Because it's 32 degree is special for the ski jumping, the flying gesture training. The second one, 11, is for jumping training, and 0 is general use. So that's why it's special. It's built by Aerodynamic Research Institute, yeah, similar like the little brother one. Okay, a big brother. Big brother, we have 1 wind tunnel in Beijing. I don't have pictures. I don't have locations. That's false. Okay, it's huge, powerful, fully loaded. It can hold a real bobsleigh. Just now we mentioned that Australia uses a 50% scaled model, and we can do full size, all right? And it's looped wind tunnel with an open work section. You can see this is outlet and this is work stage. So we have done a lot of work on it, and it has 6 component balances and a power of the rolling stage. Okay, some rolling stage is not powered, and well, it's driven by athletes or others, but this one has a powered. Okay, so this part is totally different now. And to solve the supporting structure, we 3D printed a lot of mannequins. They are very expensive. Okay. All right, so although the training looks a little bit stupid, but actually it's really, really hard because over 20 meters per second, glasses will fly away, directly fly away, yes. So they have to, against the wind, and do the technical skills training, okay. So in Tsinghua, what do we have in Tsinghua? We have our own box balance, 6 components. It's specially designed for sports. You can see the loaded design. Y direction is the weight, is 150 kilogram. Z is the lateral force, the side force. Side force is really small. It's 2 orders of magnitude difference. It is really hard in the design and the manufacturing, okay? Looks nothing, but here, 1, 2, 3, 4. This is 4 sensors, and the other side another 4. How 8 sensors give out 6 outputs? We have this transcendental equation with 27 parameters, and it has to be run 7 times to give out 1 number. I use question mark to hide the parameters. Sorry for that. Okay. So 27 parameters, and look at this list. Each one is different. So we have this system running 4 years ago. We already have this, okay? So for force measurement, we don't have any problem. And moreover, we have another system of balances. It's variable. It can be used on track, and also can be used in the internal test. You can see for skeleton, this is assembly GIF, and this is for the cross-country ski, all right? It's different from the box. Each unit is 3 component, and we can calculate the 3 torque by math, okay? So it's a system, it's not a single box. These are main types of balances. All right, so that is what we have today. Then we talk about air drag. Then we use wind tunnel. Okay, air drag, especially in the air drag in the sports, it can be separated into 2 parts. One is pressure drag, the second is friction drag. Okay, the pressure drag, you can see the high pressure times high pressure area minus low pressure times low pressure area. So this is from our origin of the pressure drag. So we can make this shape into airfoil shape to decrease the low pressure, or we can use steam pulse to decrease the low pressure area. Okay, there's 2 ways. The other one is friction. Friction is positively correlated with speed gradient. Okay, but this part is not very important in sports. It's very important in the aircraft, but not such important in the sports, so I will not go into it. All right, so we always talk about racing. What's the relationship between racing and drag? In racing, we talk about speed. In speed, acceleration, we have to get the driving force, and resistance force, also the drag will decelerate it. Okay, for driving parts, we have human driving part, like skating. We have potential energy driven, like downhill skiing. And athletes' skill can affect this efficacy, okay? So there are 3 parts to determine the driving. So in the human driving, we have to improve the body limit. We have our national system athletes training. We have our body strength training program. All right. For potential energy, the major issue is a safety issue. Truly, it's a safety issue. For skills, to be honest, our athletes is not very experienced in the winter sports. Most of them are even summer sports athlete and retrained into winter sports. So we have international exchange program, and we have scientific training. All right, for the resistance. Resistance mainly comes from 3 parts. One is the equipment. Second one is posture. So how to pose yourself. And the third is team formation. All right. The first one, equipment, contains a special one as solid-to-solid friction like skate and ice. And the other 2, the mainly solid flow friction is solid liquid, solid gas, and it's flow phase. Okay, solid flow friction and the pressure drag. So to solve them, we have wind tunnel for experiment, and we have computational fluid dynamics for simulation. Later, you will see a lot of CFD result. It's as important as wind tunnel. All right, so we have applied this roadmap to all the winter sports already. Take example for the drag analyzation. First, the human-driven type, skating. So head, arm, leg, this part are pressure drag. Shoes and ice, solid friction. And on the gesture, mainly is solid gas friction here. But as I said, this part is very small and it's not the main target of our work. Second, potential energy driven, the downhill skiing. We can see the pressure drag of the because of the body shape, and the solid friction between board and snow. And here, there's almost no, I should not say there no existed, but it's really, really small. Yeah, okay. It's really small for the frictions. Okay, so now we get an idea. Pressure drag is the main part. How do we deal with it? In pressure drag, the classical model is a flow around a cylinder. So in 2D model, we can just like a circle and it's a flow. One thing I have to introduce to you is Reynolds number. Reynolds number is the most important thing in flow dynamics. Okay, so it's inertial force over viscous force, speed, typical length, viscosity. Why it's important? Because no matter it's air or water, we can always use the Reynolds number to define it. So with Reynolds number change, it will the jet trace will change from here like this, here and here. Very important one. So around 3 times 10 to the out of 5 here. The jet trace changed a lot. From here common to here, and laminar flow outside, turbulence inside, and go back to the turbulence again. So it's an important part here. From the coefficient of drag, we can see at certain Reynolds number, it dropped a lot. Suddenly dropped a lot. Because here, we have this laminar flow and the separation. When a flow leaves the solid surface, we call it separation. The flow separation is delayed, so low pressure area is smaller. That's why the CD dropped suddenly. But it will go back again, but already smaller than before. So this is critical Reynolds number. That's what we are looking for in the drag reduction. For sports, we have typical speed of skating, short track speed skating, bobsleigh, skeleton, alpine skiing downhills, alpine slalom. And we have head, length of head, arm, leg, and we calculated the Reynolds number. We found it's about below. It's just below the critical Reynolds number. So we have to increase it so we can get this benefit. How to do that? With those dimples. We use dimples to stimulate the turbulence. Here we stimulate the turbulence and make the momentum change. So the local Reynolds number will go high, will go over the critical Reynolds number. So this is CFD, it's a CFD model. We have this diameter of 3 millimeter, depth of 0.6. We have a bunch of different 3D models, and these are just 2 of them. We use this one because their dimple density is different. Dimple density defines center to center distance. So the dimple density is different. In the calculation, over 50 meter per second, we got the signal of critical Reynolds. We got signal of critical Reynolds numbers. And with increased flow velocity, area of straight jets decreases. So this is signal of critical Reynolds number. In wind tunnel, we have the similar result. We really build a lot of cylinders with that structure and put into the wind tunnel. We tested, we found that denser, more dense dimples have earlier critical Reynolds number, but it goes back higher. And for the same density, we found that interestingly, 0.3 has smaller CD than 0.7. Why? Because here we have another additional pressure drag on the dimple structure. Yeah. When the airflow goes this way, here we have a low pressure, here we have a high pressure, and they generate additional force. That's why everything should not be too much. Okay. And now we have this density and depth, so we can calculate it. We can calculate the correct dimple structure for athletes for different sports. One of them, like example, this is our wind tunnel test, and we have this chart. We have this arm, leg, waist. We have this typical Reynolds number, and we can calculate the dimples which should be used on the racing suit. This is how we do drag reduction suits. Also, we developed the dimple imprinting technology, so it's not limited to the materials, not limited to the thickness. And we have this test result, and with cooperation with Beijing Institute of Fashion Technology, this suit already got into the field. Okay, and they already use these drag reduction suits in the matches. Okay. Now that is the basic principle of the air drag. Let's go to the first example, track cycling. First, we do the 3D scan and build the 3D digital model of the athlete. By this model, we can do gesture change by computer. We can save a lot of time for athletes. Okay. Here's the velocity nephogram, and the other one is the streamline diagram. We can check the pressure, we can check the speed, we can check how the wind goes through the body. Based on this, we defined the system to describe the gesture. The first one, head angle. When head up, it's positive. Second one, height difference between head and back. A difference between head and back. The head is over back, it's positive. Okay, 头高于背 is positive. The third one is arm angle. The angle formed by upper arms. When you open arms wider, it's positive. Based on this system, we do a lot of wind tunnel tests. This is one data set. We have a lot of gestures, but how to analyze it? It's very complicated because gestures change, handles change, cadence change. So we do normalization. We do normalization for the gesture parameter, and we use an analyzation model to fit it. What do we have? We have this number, okay? Suddenly, a bunch of data came to a single line. All right, we have X with different K1, K2, and K3. We found that short helmet has with lower handle is not sensitive to the head. 0.04 means no matter your heads up or heads down, it doesn't affect your drag too much. However, if we change to high bar, the high handle is just 2 centimeters higher than the original one. And suddenly the constants jumped from 0.04 to 0.38. And the arms is changed from 63 to 20. That means with higher bar, it's sensitive to the head, not the arm anymore. Okay, and we can see this one. This line is the higher bar. This line is a regular bar. We found that it can give out the smaller drag at the best situation. All right. So this means we can use this equipment build to achieve better performance, but it's harder. Okay, it's harder because it's more sensitive. to the gesture. So based on this, we give a priority list for the future of track cycling. The first is safety. Yeah. Even this year in Tokyo, some athletes got hurt. Yeah, in the finals. The second, performance. Performance is the driving power. Driving power is determined by the body strength and the gear selection. Third, the drag reduction. So we should take this first, and then it's the fitting training. Before, it's always bicycles fits athletes. Now we're gonna change the game. Bicycles gives out the best potential of lower drag, and athletes go to fit it. Yeah, this is what they are doing in United Kingdom. Okay, so we hope we can change this training model. And in team, we found that when two riders get together, this is pressure, this is velocity. They have a lot of low pressure area. However, the second rider, they goes into directly behind the first rider. His higher pressure will immerse with the first lower pressure. So both of them enjoy the drag reduction. This is a situation that the second rider directly follow the first one. In case we have to do a offset, for example, 0.3, this trend is totally changed. We found that you get closer, both of you enjoys larger drag, but after a distance back, you can reduce the second one can reduce their drags. So it's a technique to get over, yeah. And also you can find troubles for your competitor. Okay, based on this, we have the most athletes in our test have a negative K1, positive K2, and K3, which means in the current equipment build, everyone should head up, and should get flatter, and should narrow their arms. Okay. And long helmet and the higher bars makes the drag more sensitive to head angle, so we have to we need the fit training. And also we cooperate with Shanghai Research Institute of Sports Science and the Tsinghua University, so we try to build our own racing suit. But because of time, we didn't make it. We have some prototype, hope we can use in Paris. Okay, and we do the suit optimization in the wind tunnel. Finally, Zhongtianshi and Baoshanju, they're champions in Tokyo. All right, it's second champion of Zhongtianshi. First one, we ran it in Beijing Jiao Tong University, and now we run it in the new wind tunnel. Okay. Also, we are trying to make a new track back ourselves. Yeah, now we are buying track backs from Luke. In real, it's called R96, and this year is Tokyo 2020, so it's T20. The Pardos is a company of Taishan Group. Yeah, we cooperation together. I designed the aerodynamic tube, and they manufacture the whole bike. We found that Pardo's bike is already better than R96. Yeah, we are already better than R96 and slightly behind T20. So, and this is Li Huishi from Hong Kong, China. Yeah, this is Li Huishi from Hong Kong, China. She already used this bike since last year. Yeah, but our national team still use T20 this year. Some of them are still using R96. Okay. So this is our work on track cycling. Next, we'll talk about rolling and canning. You may be interested. You may be questioning that these are on the water, right? Why we do wind tunnel? Because in racing, we want to optimize every single hair. Yeah, we want to every single Newton's drag be reduced. But there are problems because boat is too long. It's really, really too long. Even our big brother cannot hold it. Okay, 8 meters. And the work section is already 8 meters long. It's already huge, but boat is 9.4. It's double. If it's 8 people rolling, 8 people rolling boat is over 19 meter. Okay, so it's too heavy. It's too big, too heavy. And rolling, actually, the weight center of athletes is changing. It's always changing, so it could break the balance. What we can do, we cut it. Yeah, a very expensive boat, we just cut it. We cut it down, and only carbon part being placed on the wind tunnel. And we do have to reinforce it because we cut it and we break its structure. The carbon fiber cannot hold people's weight anymore. So we have to reinforce it. We design the fairings to cover the brake part, to cover the balance, to get the accurate data. And it finally can put onto the balance. Okay. And this is experiment setup. We have double rowing, rowing, single rowing, canoeing, and kayak. This is the wind test speed. For double rowing, we do catch the water, drive, and return. We do 3 technical gestures. And we tested the different wind speed. Very interesting thing. Shall I bend my back? All right. Usually people say, well, I want to smaller the low pressure area, so I want to shrink my size. Yeah. Is it true in rolling? This is straight back. And this one is correct, technically correct in the rolling. It's good to give out performance. And this is wrong, but it has smaller projected area. Interestingly, in the test, we found that the right technique is good. 10% difference. It's really big, okay? So that's why I use this word here. Not very polite, okay? Empiricism, yeah. Should I bend my back to empiricism? Actually, no. With wind tunnel, science data is a new fashion, okay? To team formation. So when athletes on the boat, everyone have their performance, but seats change can cause a lot of different. So here we have A at the front, B at the back. It's solid line. The dashed line is B in the front, A at the back. Then what do we have? Big difference, 10 to 30% difference. So B plus A is good, then A plus B. 2. They are champions. Yeah, in Tokyo, yes. And for men's double rolling, double canoeing, similar experiment. A plus B is better than B plus A. They're silver medal, yeah, in Tokyo. All right, that's why wind tunnel test can also benefit the water sports, okay? And also by Reynolds number simulation, we can do wind tunnel test for swimming, yeah. Like I just said, Reynolds number is very important because it can describe almost all the fluid, yeah. All right, the sixth one, the sixth part. The sixth part is winter sports. It will be very brief, okay. All right, ski jumping. I mentioned ski jumping many times because it's too dangerous, yeah. So people jumped at about over 90 kilometers per hour. At this speed, jump up, fly, get down, okay? So maybe there are only 1 or 2 seconds that he's flying in the he's flying in the air, no time to thinking. Yeah, really no time to thinking. And statistics tell us each athlete can only perform maximum 6 fly or 6 jump per day. Otherwise, it will get hurt. Yeah. What do? We have this wind tunnel, special wind tunnel. We have this AI posture recognition synced with force balance. So we can train the athlete in the wind tunnel how to jump, which direction, okay? And we can train them to get familiar with air. They can control their body in the air, and they do not have to think anymore. Also, we do the gesture, the posture optimization, team formation for skating, for downhill skiing, for skeleton, luge. Again, very interesting. Shrink down doesn't make it better. Yeah, here. Shrink down doesn't make it better. Bend the back too much. They will generate additional pressure drag at the back. So we break the empiricism again. I talked about a lot of CFD. Is it trustable? The answer is yes. We have this PIV test. PIV test can visualize the flow field in the wind tunnel. It's experimental tools. And this is CFD result. This is PIV result. But analyze the flow field, we found they are highly agreed with each other. So as long as we give the right model, right calculation setup, right math, CFD can save a lot of time. And CFD is really helpful because we change the body with computer. We change their arms with computer, change the distance. We don't have to occupy the time of athletes. All right. So we do team formation. This is the team formation CFD simulation, and we check this all this number with PIV. Okay. So sorry, I cannot give too much details about the wind sports. You know why, okay? Let's go to the conclusion. Conclusion, what a wind tunnel could offer in sport? We just mentioned posture optimization, equipment evaluation, team formation. Equipment evaluation, actually the track cycling team, all the equipment we are checked in the wind tunnel. Yeah. Simulation training, we like ski jumping, okay? We confirm our brake empiricism. It's very important. Second, what should we pay attention to in the wind tunnel? The first one is safety. Yeah, every time we start a wind tunnel test, I will ask my students, say, clean the ground. Yeah. Even a nail goes into the wind and it's a bullet. It's very important, very dangerous, so safety issue. Second, speed and turbulence. We have to check, the speed because temperature, humidity can affect the real speed. And we have to check the block ratio. Yeah, make sure this wind speed is accurate. Rational experiment setup. Mainly it's talk about the supporting structure. Sometimes it's badly designed or the 3D printed model is shaking, then the data is not trustable. Okay, the consistency and repeatability. So because we do racing suit optimization, every time we have to disassemble the model, we put on clothes, put it onto the workstage again. So consistency is a big problem. Repeatability. Repeatability is a big problem. Different wind tunnels, they cannot compare their coefficient of drag with each other. You have to remember that. Yeah, so one project should be keep in the same wind tunnel, and it should be run over as soon as possible. Yeah. If you change a wind tunnel, only trend is increased or decreased. This trend can be compared, but the number is not comparable. Okay. So coefficient of drag is depend on the wind tunnel that we use. This is consistency and repeatability. What can we do? We can try to develop new training methods based on the wind tunnel. We can develop new equipment. We should more technologies from aeronautics and astronautics. Yeah, we should get more tools and use in the sports. All right, so let's please let me introduce our facility. Yeah, our lab. The State Key Lab of Tribology, SKLT, is founded in 1986. It's under the Department of Mechanical Engineering. Professor Wen, Chen, Luo, Meng, and now it's Professor Tian is the chairman. So I'm working on the surface interface science and the property control in machinery. Oh, sorry, we got this one. Very lucky. It's 16 units per all over the world, all over the country. Professor Wang Jiadao is our team leader, and it's me, Professor Lei, and Professor Ma. And we work on the drag reduction and self-assembly manufacturing. Okay. These are our cooperator. So we have this, many universities, research institute, and companies. So everyone works really hard for Beijing Olympics. Thank you very much.